It is a review for exam number 2. We'll try to solve a set of old exam problems. Number 1, mark each statement true or false and justify your answer. A and B are 3 by 3 matrices, then their product is given in this way. Is it true? It must be false. From the definition, the product of AB is given in this way: A, B1, and A, B2, and A, B3. That means that in metric multiplication, the first column is made the metric A times vector, the first column of B, and second column in the product is A times the second column of B, and so on. That's the definition. So given one is wrong. The metric is invertible. To check if it is invertible, you may try to count number of pivots. Okay, now we'll apply elementary row operations. 1, -1, 2, 0, 1, 5. For this pivot, we eliminate that one. Twice addition will be 0. Twice addition, it will be 0 again. Now that becomes 4. We have here 3 pivots so that it is invertible. If A is a 4 by 4 matrix and column space of A is the same as the R4, whole R4, then AX equals B has a unique solution for every B in R4. Okay, the column space of A is R4 means that this one has a solution, and that is because it's a square metric, and that means the metric multiplication is onto, so that also it must be 1 to 1. That means the solution must be unique. Okay. So it is true. Each line in Rn is a one-dimensional subspace of Rn. Is it true? It's wrong. And line passing through the origin is a one-dimensional subspace of Rn. However, for example, in R2, the line is not passing the origin, then it is not a subspace because 0 is not included in this set. So it's not a subspace. A is a 4 by 4 matrix, then determinant of Ka is 4K times determinant of A. It is also false. Now, a row of matrix is scaled by K, then determinant must be scaled by K. Now, this is a 4 by 4, so Ka means each row is scaled by K, so there are 4 times scaled by K, so that this 4K must be K to the 4, then it is true. Suppose A is in an m by m matrix, and there exists a matrix C such that CA is identity matrix, and we want to prove that M is larger than or equal to N. Okay. Now we start with AX equals 0, the homogeneous system, and from here we multiply C, CA, and X equal now C 0, so that it must be 0. But CA is identity, so we can get here X equal 0. That means the homogeneous system has only the trivial solution. That means if we draw the matrix, then here each column has a pivot position, and for homogeneous system, if it has only the trivial solution, that means there is no free variable, which means each column has pivot, so that now for here n column, we have pivot n pivots, and in order to do that, here the m must be larger than or equal to n. If the matrix is flat like that, then here, so that the number of pivot cannot be larger than m, and so that at least one, the column has no pivot, so it is impossible. So from here, we can conclude m is larger than equal to n. Right? Okay, so that we prove that. Here, find the inverse of A. Okay, now for this problem, you may start with your A and I, the identity, the augmented matrix, and apply elementary operations so that you can reach here identity. And now then second portion must be a inverse. In this way, you can find it. Rather than the hand computation, let's see a program. Okay, here. Okay, that is for number 3. I implemented here A is defined. Now AI is made, and we try to get reduced echelon form of the augmented matrix. Then now execute. Okay, F5. Okay, execute. Then we can see from the command window. Okay, here the result of number 3, A and I, and then this became identity. So this portion, 3 column, the second half of this augmented matrix is the inverse of the matrix A. Okay. Now, for this one, find the LU factorization of B, and here we have U matrix. Now, also for this one, number 4, okay, here for number 4, and B is the defined, and we try to get LU factorization, so that L is given in this way, U, and I put on the document, and you have to do this one manually, and you have to understand how you can get ln u LU factorization. Okay, now try to do it yourself. Okay, this is the solution for LU factorization. Okay, let's go to number 5. The following displays a matrix A and an echelon form of A. We want to find the basis for column space of A and a basis for the null space of A. Okay, this is an echelon form, and we can find the pivot position. So 1, 2, 4. So basis for column space A is these 2 columns and pivot columns. Okay, there's a pivot column, this is pivot column, there's again pivot column. So here, in fact, pivot position is this one, that one, and this one. So the corresponding position in matrix A is the pivot positions. Okay. So column 1, 2, and 4 are bases for column space of A. Now, to find the null space of A, basis for null space of A, we have to solve AX equal 0. So we have to apply further elementary row operations to reach at the reduced echelon form. Okay, so from here, from there on, okay, here now we have to eliminate that one and change this one 1, so it becomes the elementary, becomes the reduced echelon form. Okay, so twice subtraction, 1, 0, minus 2 and 0, and 0, 1, 5 over 2 and 0, and 0, 0, 0, 1, 0, 0, 0, 0. Now it becomes the reduced echelon form. Here, leading 1, leading 1, leading 1. Okay, from this one, now, from the first one, it is same as x1 equals twice of x3, and x2 from the second row, same as minus 5 over 2 x3, and x3 is a free variable, so x3 equal x3. Now how about x4? x4 must be 0. Okay, so from here, now we can get the solution x, x1 to x4. They're the same as, along with the free variable x3, the vector is 2 minus 5 over 2 and 1 and 0. So in null space, the vectors are in this form, and for some choices of x3, so that this will be a spanning set, and alone it becomes a basis, right? So basis for null space of A is this one. Okay. Number 6, let A be a 5 by 7 matrix if the subspace of all solutions of AX equals 0 has a basis consisting of 4 vectors. That means now nullity is 4. What is the rank of A? The rank theorem says that rank plus nullity must be same as n number of columns, so that immediately you can say that is a 3. Right? H is a span of V1, V2. Here we have a V1, V2. And B is now V1, V2 the set. And find B coordinate vector of X. That means that here we have to find the coefficients so that C1, if we try to write down here, C1 V1 plus C2 V2 is given vector X. So we have to find the C1, C2, then this one will be the B coordinate vector. Okay, so for this problem, you have to solve the augmented matrix and try to find the solution. Okay, let's see the result. For this problem, we have the augmented matrix, and we applied. Okay, let's see here. For number 6, B, that is augmented matrix, and try to get reduced echelon form. Then that's it here, so that the solution is 2, 3. Okay. So here, this is the same as here now, 2 and 3. That's the answer. Okay. Just try to solve this problem using your paper and pencil. Number 7. find the determinant of a to the 3 where a is given. Now for this problem, what we have to get is determinant of a cubed. Now, do we have to get a cubed? No. Here the property of determinant is given in this way. And for example, determinant of product of two matrices is same as the product of each determinant, right? So the same way here, a times a times a, so it is same as now determinant of a and here cubed. So we have to find the determinant of a, and we try to get the cube of the number. Okay. Now to get determinant, we have to use coefficient expansion. Now this third row has 1 here and 0. So let's try to use this coefficient expansion and eliminating and row and column, so that here determinant of a is the same as 1 times minus 1 to the, for this position is 33 position, and determinant of the sum matrix and 10, 13, and 1, and 1, 0, 0. Okay, and then 1, 0, 0, and 20, and 0, minus 1, right? Okay. Now, so that, okay, this is 1, that is 1. Here, to find this portion, again, we may try to use that second row expansion. Then this is 1 times minus 1. Okay, so that, okay, this is 1, we know. And for that one, now 1 times minus 1 to the, here 2 plus 1, right? And then we eliminate, okay, row of this one and column, so that now it becomes determinant 13 and 1 and 0 and minus 1. Now for 2 by 2 matrices, determinant is AD minus BC. So this is minus 1 and that is minus 13, so that determinant of A must be 13. So here the final answer must be 13 cubed. Okay. Number 8. Now W is a set of ABC, and ABC satisfies these two equations. For this one, we may write this one so that we want to find the basis. Okay, for part A, okay, that is, we write down these two equations in this way: a minus 3b plus c equals 0, and b minus 2c equals 0. Then from this one, once we try to write the system in metric form, then here 1, minus 3, and 1, the coefficients metric, and then second one must be 0, and that is 1 minus 2, and this is now A, B, C, and then here right side must be 0 and 0, right? That is matrification. Now, to find the basis for W, we have to solve this linear system, so that eventually this is same as null space of, if we call this portion A, then null space of A, right? So here, from this A, we apply elementary row operations to reach at the reduced echelon form, and we can find the solution for basically ax equals 0, right? Okay. 3 times addition makes 1, 0, 3 times minus 6, so that there's minus 5. And here 0, 1, minus 2. x1, x2 are basic variables, and x3 is a free variable. So from here, x1 equals now 5x3, and x2 is 2x3. Now x3 is the free variable x3. So from here, x is same as now x3, free variable, and then direction is 5, 2, 1. For arbitrary choice of x3, the x will become a solution, so that the w is the collection of the solutions of that system, and so that eventually this one becomes a basis for w. Okay, the null space of A. Okay, that's the basis. Okay, now there's only one vector, so that dimension of w must be 1, right? Okay, that's the end of the review. Thank you.